So our next speaker is Viviana Bono from University of Torino, and she will be telling us about a typed approach to ontology manipulation. So take it away. Thank you.
Thank you. First of all, I want to apologize because this is not going to be an easy talk to me because I don't have any voice. Sorry about that, but I hope to convey enough information. And second thing, this is not a technical talk, neither a formal one, but just more like a vision, and I hope that you don't get too bored about it. So, let me tell you a story. An ontology is a formal explicit specification of a shared conceptualization used to represent knowledge about a domain by defining possibly uniformly its concepts and the attributes and the relationships among concepts. The idea is to have a common vocabulary to talk about a certain domain and enabling machine understanding and reasoning, but not only, also human one, and facilitate knowledge sharing and data integration. So that's very important. Talking about ontologies. I'm just recalling some concepts that I'm sure every one of you knows about RDF triples, for example, that are made of a subject, a predicate, and an object, and each component can be an international resource identifier describing a resource, indicating a resource that describes a certain concept. So we build graphs by connecting those components, and this is a very Italian example. Margherita is a pizza, it's a type of pizza, and it is eaten by vegetarians mainly. Oh, sorry. Sorry. Then I'm sure you heard about OWL that builds up RDF, but is a richer language where basically knowledge is separated into two parts, two boxes. One is the T box that defines the vocabulary of the domain, in particular concepts and their relationships. Very important relation is the subconcept relation, similar to a subclass relation. And then you have A boxes, where you have assertions about individuals, for example, the fact that Margherita is a pizza, or that Gianni and Margherita are connected by a eat link. The OWL language allows you to infer properties starting from the two boxes, A box and T box. And I mean, this is a very simple inference. It's like OWL works on a subset of first-order logic. And I'm sure you can see the example by yourself. You can infer that Margherita is a vegetarian pizza because it is eaten by a vegetarian guy called Gianni. Another ingredient is XML. XML comes in various forms, and we have here two examples, RDF XML and OWL XML. RDF XML is simpler, and this is the one we used actually. And you can actually express triples as I showed before. Instead, the OWL XML is more richer, sorry about. For example, here you can see that in the RDF, pizza is actually a tag, whereas in OWL XML, It's actually an IRE, an attribute of a class, so it's richer, is a richer explanation, at least in the syntax. We choose the simplest one, RDF XML, because it's the one that should be supported by any tool working on ontologies. I said already that the OWL XML is richer in syntax, but from the point of view of the expressiveness, by reification, you can basically express the same things, because you can make a verb like a subject and create a triple with a verb as the subject, as a noun, so to speak. Oops. Why am I talking about all these? Nowadays, inference is done preeminently by machine learning tools, where you actually feed the assertions to which is, you know, the propositions about the individuals to machine learning tools, and you get results, and you don't do inference in a logical way. Well, not that much anymore. So we were talking about colleagues that actually worked on knowledge representation, and they felt like there was a loss of expressivity by doing that. And so we started, it's my undergrad students, now master students, and myself, started to wonder if functional languages could actually support and enhance the standard classical well-known knowledge representation inference. And in this sense, we explored the use of C Duce. We have in the audience one of the fathers of C Duce, actually. It was born from a collaboration between groups in France. And what I like about C Duce is that it's actually a general purpose language, very fun to program with. And this goes beyond the fact that it's XML-oriented. I will tell you about that soon. It's XML-oriented because it gives a very rich pattern matching in order to check and build XML. So we thought maybe we can use it to work with ontologies with some success. First of all, on my right, there is a fragment of XML code describing a parent book, meaning people with children, and these people with children have a name and possibly a phone number labeled with home or work, not necessarily like that. And on the other side, there is the version of XML written in C Duce, and here you have basically the components. You have a tag, and here you see you have a gender, and then in squared brackets you have a list of elements that characterize your tag. What is parent book? Parent book is a type, and what does the type do? When we upload the XML file, basically this is checked against the type, and if everything goes well, then C Duce produces its own version of XML, the one on my left. So just have a look. You have angular parentheses to contain tags and attributes, and then square brackets to contain to contain elements. For example, here in this parent book, you have a person of F gender called Clara with no children and a phone number without any label about the fact that it's home or work. And instead here you have Bob, and that has at least, that has one child, F, called Alice, with no children, and a phone, which has an attribute home, which was optional, but this is what it is now. So again, this is summarized the syntax, which is not only of the language, but also of the types. You have tags, attributes, and content, where tag and content are types or type patterns. As I said, pattern matching is very beautiful in this language. So now we go to the type the XML was checked against. And here you have let's go through a couple of things. One good thing about the C Duce types is that they are readable, humanly readable, and easy to understand. But basically, a parent book is a book made of a zero of more persons, and then you have F persons and M person. F person is a person with a tag person with an attribute gender assigned with F, and the rest, and similarly for M person. Then we saw the children have names, have a name and some other data. PC data represents a string, which in turn is simply a sequence of characters. And this is important in C Duce because it means that we can stick together generated strings by the program with XML already there. You have all kind of regular expressions. For example, here you have an alternative between home and work to describe the phone, and this is to say, well, it is to say that I don't remember what's that. It's optional. Thank you. Yes, because now I was getting confused with the other use where you have the non-greediness. But it's okay. Thank you. It says that, in fact, I said before that it was optional. And the rest should be quite clear because you have a normal way of forming, for example, emails with the character between sets of chars. As I said, we have types, concatenation, union, one or more times, zero or more times, and then the optionality, 0 or 1 time that I wasn't remembering at the moment. So sequences are really the core of the type system of C Duce. Let's see now other two ingredients. Functions are lately bound overloaded functions that are typed with the form of intersection types, which is another very interesting thing. And this is the form. Basically, it says that if we have an argument of type T1, we get S1 as a type for the output, and so on and so forth. And each of those clauses are a pattern that gives us an expression of a certain type when the type corresponds to the type I was saying, I was mentioning about. I didn't say it very well, but anyway, overloaded function, so the type determines the branch that it is going to be executed. And we have map and transform that works with sequences, and map is the usual map that transforms each element recognized by a pattern. And then we have transform that instead is filter and transform. Basically, map gives you back as many elements as the starting sequence, instead transform, it can give you back a shorter sequence. So let's see a couple of examples. Here you have a transform because you want to have a concatenation. Oh yeah, another difference is that transforms returns a sequence. Here you want to have a list of names taken from the parent book. And so you basically bind, and we will go back to this underscore, which is the white card as usual. But you bind the person from the parent book, and for each of the person, you basically, by pattern matching, extract the name, and you concatenate it to the names of the recursive call. What is very nice here is the use of this union type, because basically it says, well, we have to extract also the names of the children, but children is another tag, it's not a parent book. So what do? We simply do this. We put a wildcard here to say that this transformation is okay both for parent book to take the first level of the names and for children that are another tag. Okay. Then we have this intersection type use. This is a simpler example. Basically, very, very normal example. According to the type of the arguments, you can have either a sum if the arguments are int, and otherwise a concatenation of strings that is represented by at. Here you go by pattern matching, meaning that x and y are the argument, the actual parameters, the formal parameters, the function that will be bounded to the arguments according to the one. So this function has types, couple of pair of int, arrow int, and couple of strings, pair of strings, arrow string. And now another example, which is a bit more complicated. I go back to the type I showed you before. Now the idea is to actually specify better information about people. In particular, we want to have men and women as tags, not as attributes, gender F or of M. And we want to have name not into the elements, but as an attribute. And so we basically manipulate the ontology, the data structure we had before in order to get this. So what do? We write a function that is called split, and split as an intersection type because it takes either an M person and it transforms it in a man, or an F person and transforms it in a woman. And another very interesting thing here is, okay, let's read this first. Here, by pattern matching, we extract the gender of a person, the name and the children to apply recursively the transformation. Was it me?
No, the other room.
Okay, thank you. Then I was saying it's interesting because you can see here that tags are actually first-class values because we generate an XML element, and actually we give the tag inside the program, because if the gender is matched with the F, this new tag called oh dear, either man or woman will be appear here in this new element we are generating. So a good thing about C Duce is not that only allows you to check XML, but allows you also to generate it in a well-formed way. So basically here what happens? It happens that for each tag M or F, we create a new element in XML with the name as an attribute, and then we recursively call here the function map. It's important that this is an intersection type because it allows you to specify the type of S and D that are going to be partitioned in sons and daughters, where sons S is of type sons and the other one is of type daughters. If we add a function person, it's not visible, person, arrow, man or woman, we wouldn't been able to type the recursive call because for each S and D sequence of male, sequence of female, we wouldn't been able to have a specific man or woman type, so we weren't able to find the right type for daughters and sons. What did we do? We basically wrote a type to describe an ontology in RDF XML. Of course, we have namespaces. We need namespaces in order to define each tag in a unique way, in a way that, I mean, the W3 does. So the string before the colon is actually the namespace, but just to go through quickly, we have an ontology has a certain tag and with certain attributes and values. It is a set of 0 or more things. Things can be ont, which is the reference about the name of the ontology, properties, class attributes that are the elements of class attributes, a notion of equivalent class, we basically left it very, very open. Subclass, everyone knows what it is, and so on and so forth. The most important thing is that in order to be able to talk about properties of individual, we left that blank because we had to, otherwise we had to hard code all the relations. For example, this underscore could be parent of, okay? Had we used the OWL XML, we would have had names for attributes for those things too. What we did was to take a thesaurus, which is basically a terminological database organized in a hierarchy, and transform it in an ontology. Which thesaurus we used? We used the Europeana fashion, which is a multilingual thesaurus for fashion and fashion-related concepts that turns out to have also historical information about garments. What we did was porting from this thesaurus to an ontologist and then do merging of ontologies. Sorry. Maybe, yeah, I should go a bit faster. The thesaurus is simpler. The thesaurus basically has concepts which are under the type desk, and the attributes are labels, scope notes to specify better certain characteristic of the concept, exact match that sends you to the resource where basically the element is defined, by the resource string, usually an HTTP site link. Then broader is the superclass, and type is actually the name of the superclass inside this is a typo, shouldn't be green. It should be black, but I wasn't very good with my LaTeX, so it became green. Sorry about that. Instead, an ontology is a subset of what I've showed you before, and we decided to take as much as possible from the thesaurus, and we have, maybe it's better to show you some transformations. At first, we had simple functions in C Duce to transform notes from scope note, which is a label of the thesaurus, to note, which is a label of an ontology, exact match to dictionary, broader, I said it's subclass, and so on. But then we decided to write a function altogether that does all those things. So basically what it does, it matches a thesaurus. This is the sequence of thesaurus that are bounded by concept. And for each concept, we create a new class. The name of the class, it's taken from the description of the concept, and it is the string about, and the value of the string is about, which is about. And the rest is quite simple, because some of those are simply matched exactly. They are matched and returned as an identity function. The only nice thing is this thing that broader is translated as subclass. And all the attributed are linked together and put in at the right place, and then the new class is actually concatenated with the rest of the classes. The result is a result. Then we did a bit massaging by using protégé, because we had basically three ontologies separated, and in particular, we had the fashion objects that were not connected to materials, and to us it was important to have a relation between fashion objects and materials by a relation called made of, that will come in a minute. The question could be, could we have done this by using C Duce? Yes, but it was a quite long and boilerplate code, and so we decided to use protégé instead. Because one of the goals is also to support protégé. Protégé doesn't use types, so you do manipulations without actually checking types, instead C Duce does. Merging is really a word that means a lot of things: reciprocal enrichment, translation of ontologies, merging of heterogeneous ontologies. What we wanted to do is actually to do an example of the third interpretation, which is merging of heterogeneous ontologies. So what we wanted to show was that by using this functional language, we could have simple ontologies and create more complex ones to enrich knowledge. In particular, what we did was to integrate the people ontology with the fashion ontology, and in particular, we wanted to find the knowledge representation of a 12th century society and their clothing, and by doing that, we did kind of a broad search of all the garments that were not made of artificial materials, and excluded them. And to do that, we actually used the C Duce. And yeah, what is nice about this, just a couple of things, and then I'll go to the conclusions. The function made of basically takes an individual, the ontology, and it gives back a sequence of materials. The first individual is matched against an individual, which is a named individual with an in the prop with that corresponds to made of, the label we added with protégé. So basically what we do is to look for made of, read the material, and go to get the other individual that corresponds actually to the material to see if this is labeled artificial or not. And the other one checks if a garment is made completely of artificial or not, or natural material. Then we did other things to integrate information. We had another ontology that had also information on the jobs. So we got, in the end, a very rich ontology where we knew things about how the people lived from the point of view of what they were wearing and what there was their position in the society in a certain age. What we really enjoyed was to see how easy it was to check data transformation instead of checking it by looking at pictures generated by the protégé tool. But it's actually a reciprocal support that we wanted to offer. And we hope that this starting point is a contribution to data interoperability. I'm sorry. Thank you.